Pluto, a distant and enigmatic dwarf planet once considered part of our solar system's planetary lineup, has once again captured attention, this time due to startling claims by leading astrophysicists Neil deGrasse Tyson and Michio Kaku. They propose a shocking possibility. Pluto might be on a collision course with Neptune. But how could such a cosmic catastrophe occur? And what would be the consequences of such a powerful impact? Are we merely witnessing a rare celestial oddity, or is there a deeper, more alarming reality behind this potential planetary disaster? Let's dive into the science behind this hypothetical Pluto-Neptune collision. Once classified as the ninth planet, Pluto was redefined as a dwarf planet, in part due to its unusual orbit. Yet, it remains a source of fascination among astronomers. According to recent predictions from prominent experts, Pluto's orbit brings it dangerously close to Neptune's path. Both Neil deGrasse Tyson and Michio Kaku have voiced concern over a possible catastrophic encounter between these two worlds, a scenario they believe could pose a broader risk to our solar system, including Earth. How is such a collision even possible? Pluto's journey around the Sun is unlike that of any other known planet. It takes a staggering 248 Earth years to complete a single orbit, so long that Pluto hasn't even completed one full loop since its discovery in 1930. But it's not just the length of its orbit that raises eyebrows. Pluto's orbit is highly elliptical and tilted at a sharp 17 degrees angle relative to the ecliptic plane, the flat, disc-like plane in which most planets orbit. One of the most striking aspects of Pluto's orbit is that it actually crosses Neptune's path. For about 20 years during each orbit, Pluto is closer to the Sun than Neptune. Given this crossing, it's natural to ask, why haven't the two planets collided? The answer lies in the complex gravitational interplay between Pluto, Neptune, and other giant planets, especially Jupiter. Despite the orbital overlap, a gravitational phenomenon known as orbital resonance keeps the two bodies from ever getting too close. Specifically, Pluto and Neptune are locked in a 3:2 resonance. For every 3 orbits Neptune completes, Pluto completes 2. This synchronization keeps them safely out of each other's way. Still, Pluto's orbit is far from simple. Because of its extreme eccentricity and inclination, it's sensitive to gravitational nudges from other celestial bodies. The three-body problem in celestial mechanics, the challenge of predicting how 3 gravitationally interacting bodies move over time, applies here. Tiny changes in conditions can lead to huge differences in outcomes over millions of years. Yet, simulations show that Pluto's orbit, while chaotic in nature, is remarkably stable over very long timescales. The gravitational influence of giant planets, especially Jupiter's immense mass, acts as a stabilizing force that helps maintain order in the solar system. These subtle gravitational relationships are what prevent our cosmic neighborhood from descending into chaos. So, if Pluto's orbit has remained stable for billions of years, why are these top astrophysicists now sounding the alarm? Part of the reason lies in the limitations of long-term orbital simulations. While current models suggest that Pluto and Neptune are safe from collision, unpredictable factors and minor anomalies could shift outcomes over immense time spans. This unpredictability, combined with Pluto's unique orbital features, has reignited interest in re-examining these dynamics. Whether or not a collision between Pluto and Neptune is likely or even possible in our lifetimes remains a subject of debate. But one thing is certain. Pluto's complex and beautiful dance through space continues to challenge our understanding of celestial mechanics, and the questions it raises are as fascinating as they are profound. Concerns have been raised about the possibility of collision between Pluto and Neptune, an event that, while highly unlikely, would be both mesmerizing and catastrophic for our solar system. Given Pluto's smaller size and icy composition, such an impact would likely shatter it, releasing massive amount of energy. The resulting debris could disperse throughout the solar system, potentially threatening nearby planets and their moons. For Neptune, a collision of this scale could disturb its atmospheric composition and possibly even alter its orbital path, depending on the specifics of the impact. Dr. Michio Kaku, a renowned theoretical physicist and string theory expert, offers a unique lens through which to view the scenario. His work emphasizes the deep connection between celestial mechanics and theoretical physics. Understanding the gravitational interactions and orbital patterns of bodies, like Pluto, not only informs us about potential cosmic hazards, but also improves our ability to plan future space missions, especially those targeting the outer reaches of the solar system. The study of Pluto's orbit, eccentric, inclined, and occasionally intersected with Neptune's, continues to fascinate astronomers and challenges conventional planetary models. Despite its reclassification as a dwarf planet, Pluto's dynamic role in our planetary system remains significant. Its unpredictable motion is shaped largely by Neptune's gravitational pull, which, through a phenomenon known as orbital resonance, has kept the two bodies from colliding thus far. Neil deGrasse Tyson and Michio Kaku have both voiced concerns about the long-term stability of this gravitational dance. Their perspectives highlight how crucial it is to understand orbital mechanics and planetary dynamics, not just for academic interest, but for practical applications in space navigation and hazard prediction. If such a rare collision were ever to occur, it could create extreme conditions, intense gravity, and high-energy impacts that might provide a unique testing ground for string theory. This theoretical framework, which posits that fundamental particles are one-dimensional strings, seeks to unify the basic forces of nature. The energy released during such an event could potentially produce phenomena predicted by string theory, offering insights into how particles and forces behave under extreme conditions. While the Earth would remain physically unaffected due to its distance, the scientific implications would be profound. A Pluto-Neptune collision could advance our understanding of the universe's fundamental laws and help bridge the gap between theoretical predictions and observable phenomena. Ultimately, Pluto's complex orbit and its gravitational interplay with Neptune serve as a powerful reminder of the intricate and often fragile balance that governs planetary motion. Through ongoing simulations and theoretical modeling, scientists continue to monitor these dynamics, revealing the cosmic choreography that shapes our solar system and offering valuable lessons for both exploration and theory. The hypothetical prospect of collision between Pluto and Neptune, recently suggested by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the complex and still unfolding nature of the planetary dynamics. Although such an event is extremely unlikely in the foreseeable future, the intricate gravitational relationship between Pluto and Neptune serves as a reminder of the delicate balance that governs celestial motion within our solar system. Beyond its scientific intrigue, the study of Pluto has practical implications for future space exploration. NASA's New Horizons spacecraft, launched in 2006, made a historic flyby of Pluto in 2015, capturing high-resolution images and detailed data of the dwarf planet and its moons. This mission unveiled striking surface features, such as towering mountains of water ice and expansive plains of frozen nitrogen, offering unprecedented insight into the geological processes at play on distant worlds. The success of New Horizons showcased not only significant technological achievement, but also the collaborative effort needed to explore the farthest reaches of space. The data collected has enriched our understanding of the diversity of celestial bodies, particularly in the outer solar system, and laid the groundwork for future missions to other dwarf planets and trans-Neptunian objects. Pluto's classification as a dwarf planet has also sparked ongoing debate in the scientific community, raising questions about how we define and categorize celestial bodies. While Pluto meets several criteria traditionally associated with planetary status, such as orbiting the Sun and possessing sufficient mass for a nearly round shape, it falls short due to its inability to clear its orbital path. This discussion reflects the evolving nature of astronomical classification and underscores the vast diversity that exists beyond the 8 primary planets. Studying Pluto's orbit offers valuable insights into celestial mechanics, particularly in the outer solar system. By examining the interactions between Pluto, Neptune, and other distant bodies, scientists can deepen their understanding of planetary formation and migration. These findings contribute to broader theories about the solar system's origins and evolution, including insights into the early dynamics that shaped the Kuiper Belt, a region filled with icy remnants from the solar system's formation. Furthermore, understanding Pluto's orbital behavior and its long-term stability, despite its unusual and highly elliptical path, enhances our knowledge of how gravitational forces maintain equilibrium over billions of years. Such studies are essential not only for grasping the mechanics of our own solar system, but also for identifying potential exoplanets and habitable worlds elsewhere in the universe. Though the idea of a Pluto-Neptune collision remains firmly within the realm of speculation, it serves as a powerful reminder of the universe's dynamic and often unpredictable nature. As space agencies and astronomers continue to explore the frontiers of the solar system, Pluto remains a key subject of interest, both for what it reveals about our cosmic past and for the clues it may hold about the future of planetary science.